Hello, a quick video explaining the binomial probability distribution. Simple example, we roll a dice 5 times. What's the probability of rolling 4 sixes? Well, we would usually approach this by creating a probability tree. Going to roll the dice 5 times. Each trial we've got 2 outcomes, 6 and not a 6. We've got the probability of getting a 6, in this case 1 out of 6 outcomes, and we've got a probability of not getting a 6, which is complementary 5 out of 6, and then we're just repeating that, aren't we? So we would go down and find our tree, along our tree, and multiply our probabilities together. So the probability here will be, well, we can see that we've got 5 roots to our, we need what we're going for. We were going for 4 sixes. So we would take our probability of getting a 6 and multiply it together to the power 4. And we've got 1 non-6 here. So the probability of 5 6 of getting that, and that'd be to the power 1 because there's only one of them. What's true of what we've just looked at? Well, each of these trials, these 5 trials, is independent, and each of them has the same P all the way through. And they're basically our definitions for the conditions for a binomial. There's our probability that we just saw above. Now let's start at the other end and expand a binomial of p plus q to the power 5. And we're going to get 6 terms. We're going to get our p to the 5 term. We're going to get 5 p to the 4 q to the 1, 10 p3 q2, 10 p2 q3, 5 p1 q4, and q to the 5. Here we can see this is our probability we've just worked out. If we make p equal to 1/6, and we make q equal to 5/6, that's the probability of getting 4 sixes, isn't it? And this term here, that's the probability of getting 5 sixes. This term here is 3 sixes. Next one's 2 sixes, 1 6, and no sixes. There we go. And we know that all our coefficients here effectively are choosing the number of roots. 5 choose 1, 5 choose 2, 5 choose 3, and of course we know that we can get these out of a Pascal triangle. Here's our level we got down to at 5. We've got 5, 10, 10, 5, so that's 5 choose 1, isn't it? 5 choose 2, 5 choose 3, 5 choose 4, and so that all works, doesn't it, for us? Tick. And of course in this case p plus q equals 1, so therefore p plus q to the power 5 equals 1, so the whole of this expansion must equal 1. So that's what we expect, isn't it, because the total probability's got to be 1. So here we are. We've proved then that with the maths above, that if the p stays the same and each trial is independent, we can write a binomial, and this is how we write it. X, our variable here, which is the number of sixes, is binomially distributed, with the n is the number of trials. In our case we did that 5 times, didn't we? And p is the probability of success, i.e. the probability of getting a 6, which we said was 1/6. And if these assumptions are fulfilled, we can avoid creating our tree, and we can just work out that probability there, which we can get out of our calculators, our graphical calculators, and the binomial distribution BPD function. And just below here are all our definitions that we're going to use in this function. So we need to know our number of trials, which here was 5, wasn't it? Our number of successes, well in this case we're interested in 4. P is the probability of success. Q is the complementary probability of failure, which of course is going to be 1 minus P. And for this sort of distribution, the mean and variance and standard deviation are fixed using these formulae here. Separate video on those, but we just take the values we've got above and fill them in, and therefore it means that the standard deviation is going to be the square root of the variance is NPQ. So there we have it, a binomial distribution. That saves us having to do lots of probability trees, and we can just go into our calculator and work out the values the quick way. Bye.